Hello everyone, I am Behnam Dezfouli, and in this talk I will be presenting our work titled Empirical Study and Enhancement of Association and Long Sleep in 802.11 IoT Systems. So why is it important to reduce the energy consumption of IoT devices? First, many of these devices are battery operated, and some of them also rely on energy harvesting methods to operate. Second, reducing the energy consumption of IoT devices lowers the energy bill of households and also reduces the impact of IoT on global energy footprint. There are multiple wireless technologies available for IoT connectivity. Why Wi-Fi is a particularly interesting technology. First, Wi-Fi access points have been widely deployed in residential, enterprise, and public environments. Second, Wi-Fi operates in unlicensed bands, and this means the users do not need to worry about requesting for subscription. Third, compared to IEEE 802.15.4 and Bluetooth, the data rates provided by Wi-Fi are significantly higher, and these higher data rates are required for applications such as medical monitoring, video streaming, process control, and robotics. Finally, we observed that the energy consumption of 802.11 transceivers has been significantly reduced during the recent years. Regardless of the application type, all Wi-Fi IoT stations need to perform the following operations to ensure access point station connectivity: association, maintaining association, and periodic reception of beacon packets. In this work, we study and improve these operations by using two low-power Wi-Fi boards. Each board includes two processors, where one is dedicated to application processing, and the second processor is assigned to the Wi-Fi subsystem to handle time-critical operations. The software stack supported by these boards are FreeRTOS with LWIP protocol stack and ThreadX with NetX protocol stack. The Wi-Fi transceivers of these two boards are used in a variety of IoT products, such as Amazon Tap, LG Airbane Watch, and Samsung Gear S2. In the rest of this presentation, we refer to these two boards as CYW and BCM. Before being able to communicate with an access point, the station needs to associate with the access point. This includes three steps. First, the station scans for all nearby access points by sending probe requests on all the channels. Then the station sends an association request to the access point and waits to receive an association response. And finally, the station performs key exchange with the access point. We now study how software and network configurations affect the association process. The first step of the association process is probing for nearby access points. In the normal case, the station sends probes on all the channels. We refer to this method as join. We can also reduce the overhead of this process by programming the driver to look for a particular access point on a particular channel. We refer to this enhancement as join specific. The second enhancement is regarding key offloading. During the handshake process, a shared secret key that is called pairwise master key or PMK is generated. Using SHA-1 hash function, PMK is typically derived from Wi-Fi password, SSID, and SSID length. This function is implemented in the wireless driver, and therefore it is run by the transceiver's processor. Since PMK generation is a process-intensive operation, offloading it to the application processor reduces association delay. We implement this mechanism on the CYW station by computing PMK in the application processor and then passing the computed value to the transceiver via low-level APIs. We also study the effect of operating system and network stack. This figure shows the energy consumption of association process. The left figure shows that using join specific, we can reduce the energy consumed per association by more than 43% when using FreeRTOS and LWIP. And the reduction is about 21% when using ThreadX and NetX Duo. By using both join specific and PMK offloading, we can reduce energy consumption by 58% when using FreeRTOS and LWIP. And energy is reduced by 26% when using ThreadX with NetX Duo. In the second part of this work, we focus on the overhead of periodic beacon reception by stations implementing power-safe mode. Let's quickly overview the fundamental energy efficiency method employed by Wi-Fi. Using the power-safe mode, access point periodically broadcast beacon packets, and stations are required to wake up and receive beacons. Inside each beacon, there is a field card traffic indication map, or TIM. Each station is assigned a field in the traffic indication map, and when set, that means the access point has packets buffered for the station. Once the station is informed about its buffered packets, it sends a PS poll packet to the access point to request downlink packet delivery. To reduce the overhead of beacon reception, a station can increase its listening interval and skip the reception of some beacons. The wake-up time of the station is specified as a multiple of beacon interval, which we refer to as the listen interval. In this work, we study the effect of listen interval on energy efficiency. When using the CYW station, increasing the listen interval results in significantly longer wake-ups that are in some cases even longer than 200 milliseconds. Also, this station shows a higher sensitivity to downlink traffic and interference. In contrast, when using the BCM station, increasing the listen interval or the presence of downlink and interference results in less than 10 millisecond increase in the wake-up duration. To further investigate this behavior, we'll look into the wake-up pattern of these two stations. We notice that even in the absence of downlink and interference, the beacon loss rate of the CYW board increases versus listen interval, and this is because it cannot properly adjust its timer to wake up on time. By analyzing the wake-up duration before each beacon reception, we notice that this duration almost doubles for each step of increasing listen interval. For both stations, downlink traffic and interference further increase the wake-up duration. With downlink traffic, which belongs to the voice access category in these experiments, beacon packets are delayed by the transmission opportunity of voice access category. The voice access category defines a 1.5 millisecond period, which is called transmission opportunity, and reserves a channel for communication between a station and the access point. Also, the default access category of beacon packets is background, and this has a lower priority compared to the voice access category. Therefore, beacon transmission may be delayed by the transmission opportunity reserved by voice packets. Regarding interference, beacon packets are subject to collision and loss. The main takeaway from these experiments is that increasing listen interval cannot be simply used as a method to improve energy efficiency. This is because transceivers show different overheads considering listen interval duration, beacon reception delay, and interference. After a station has been associated with the access point, both parties need to maintain the association. In this part of the work, we address three questions. How stations maintain their association with access point? What causes a station disassociation? And how can we eliminate the causes of this association? Access point functionality in Linux machines is implemented by host apt, which is a user space daemon. Associated stations need to periodically communicate with the access point to renew their inactivity timer maintained by the access point. Referring to host apt configuration, if a station does not communicate with the access point for a particular duration, which is specified by the app max inactivity variable, then the access point sends a poll frame to the station and maintains the association if a response is received. To identify the causes of this association, we use the following testbed that allows us to study the overall operation of the system. In short, this testbed allows us to monitor association from the station and access point's point of views. These are the configuration values that we use for this experiment. The value of AP max inactivity timer is 300 seconds, which is the value used by most of commercial access points. The access point can successfully poll the station every 300 seconds until around 5,000 seconds. At this point, due to link unreliability, the access point struggles to poll the station. And as we can see, the number of beacon packets that include the AID of the station is suddenly increased to 9. Meanwhile, the inactivity timer of the station expires and the station is disassociated by the access point. Fortunately, link reliability improves shortly and the disassociation packet is conveyed to the station after the next beacon instance. The station then reassociates with the access point. This scenario clearly shows the impact of link unreliability on disassociation. Even when the listen interval matches the beacon period, the internal timer of host APD prevents the access point from making enough attempts to poll the station and maintain association. Now we set the listen interval to 20. At 300 and 600 seconds, the access point successfully polls the station. The third polling at around 900 seconds fails because the access point does not hear back from the station. We observed that access point sends 35 beacons that include the station's association ID. In this case, the access point assumes that the station is no longer in range, and therefore the access point does not send a disassociation packet to the station. From the station's point of view, the station is still connected to the access point. A disassociation unaware station does not make any attempt to reassociate. Maintaining association by relying on the access point to send probes is unreliable, and this is because the station may be left unaware of the disassociation event. The identified problem with access point site probing can be eliminated by using a station-generated keep-alive messages. A keep-alive message can be generated by using a TCP, UDP, null, or R packet. Some low-power transceivers allow keep-alive packet generation without the involvement of application processor. Specifically, when it's time to send a keep-alive message, the Wi-Fi subsystem generates the message, and the application processor can remain in a sleep mode. Both CYW and BCM stations support this feature. To validate the effectiveness of transceiver-generated keep-alive packets, we utilize driver APIs to set up null packet generation. In this experiment, to verify successful downlink packet delivery, the pinger pings the station every 450 seconds. We also use 20-second listen interval to ensure association is maintained even when the listen interval is very long. As the results show, the station's inactive timer kept by the access point is renewed in about every 150 seconds, and this corresponds to a null keep-alive packet or the packet exchange caused by pinging. This figure also shows how link unreliability affects ping delay, number of packets exchanged between the station and access point, number of retransmissions, and the number of beacon packets including the association ID of the station. Regardless of the number of retransmissions, a station-generated keep-alive packet successfully renewed the association timer kept by the access point, and the station remains connected to the access point. We presented the importance of periodic communication with the access point to renew its inactivity timer. Now we exhibit that key renewal is also a time-critical operation that may cause a station disassociation. During the association process, each station is assigned two keys, a PTK for unicast communication and a GTK for multicast and broadcast communication. Both keys are periodically renewed. The GTK is also renewed whenever a station leaves the network. This renewal is necessary to prevent the station from receiving multicast or broadcast packets of the network that the station no longer belongs to. This means mobility and disassociation of any station may require the access point to communicate with all stations. In the experiments of this section, a smartphone has been programmed to leave the network every 450 seconds and join the network again after 3 seconds. In these results, GTK renewal is performed successfully until around 4000 seconds. At this time, due to link unreliability, the access point fails to renew the key and disassociates the station. However, since the station does not receive the disassociation packet, the station is unaware of the disassociation event. This problem is caused by the limited number of retries performed by the host app daemon. By default, the number of retries is set to 4. To remedy this problem, we increase the number of retries to 32. As the results show, key renewal proceeds successfully in this scenario. The main takeaway of these experiments is that key renewal may result in the disassociation of IoT stations when the listen interval is long or when the communication link is unreliable, and fixing this problem requires customizing access point configuration. In conclusion, in this work, we show that ensuring the energy efficiency of association, beacon reception, and maintaining association is essential for building low-power Wi-Fi based IoT systems. We show that association cost depends on multiple factors, including probing, key generation, operating system, and network stack. Increasing listen interval to reduce beacon reception overhead may negatively impact energy efficiency. Maintaining association by relying on access point pole messages is not reliable, and key renewal aggravates the chance of disassociation.